Hello guys, today we're going to take a brief introduction to assembly language. This will be a good review for the final. I'm going to add another video as a review for the final. Make sure you check, I think I have 6 or 7 videos also: floating point representation, big picture, binary, hexa, octal, converting between bases, adding, subtracting, how to represent characters, how to represent negative numbers. All those videos are posted, so please check them before you do this. So let's see. And here's we're gonna go back on the big picture. Here we have C, C++, Java, Python, C#, and Lisp. All of those are high-level languages, high-level programming languages. And what do we mean by high-level languages? High refers to the abstraction, and this abstraction is the concept of abstraction, meaning hidden information. How much information is hidden? Abstraction. Let's say now, do you have to be a mechanic to drive a car? There's lots of things that happen in the car that are hidden. You don't know about it. You just drive it. You don't need to be a programmer to use a computer. There's lots of things are hidden in the back. Like if you say Windows, they have they're user friendly. They have high level of abstraction. They hide lots of things in the back. You don't know about it. Low level languages like assembly, also referring to the abstraction. Assembly doesn't hide that much information. It's harder than C and C++. And here we compare it to English. High level languages are closer to English than assembly. Assembly is closer to machine language. It's in fact in between high level languages and assembly language. High level language are C out, A multiplied by B plus C. Easy to understand, user friendly, close to English. Abstraction, lots of high abstraction. Assembly, low abstraction. It's almost like English, but it uses mnemonics for the instructions like move, mul, add, call, EAX, A. So if a non-programmer looks at this, they might not understand it. That comes from the concept of abstraction. So assembly is a lower level than high level languages, close to the hardware, near the hardware, or machine language, which is 0 and 1. 0 and 1. And you should know by now, machines, they don't understand English. Their language is 0 and 1, binary. And there's lots of compilation and conversion done in between. So you write a program in C, C++, like hello world example. You compile it, checks the syntax of that program, is the grammar right, everything right. Then it translates it to assembly and into machine language or object code. Object code or operation code. And let's see here. So this code then is executed by the CPU. And what is a program? It's a sequence of instructions. Instruction 1, 2, 3. Those instructions are for the CPU to execute. So a high level language is translated to assembly, translated to machine language execution, and then it's called by the CPU. Fetch. This is the instruction life cycle, which is done by the CPU. Instruction, fetch the instruction. Decode, knowing this is a move instruction. Fetching the operand, EAX and A. And here should be not execute, not decode, it should be execute, sorry about that. This is execute, E-X-E. We execute the instruction and then we write back, or the CPU does that. Now the relation between high level languages and assembly, meaning one instruction in high level language is translated to one or more instructions in assembly, and the relation between assembly and machine language is 1 to 1, meaning one instruction is assembly is translated, so it's a regular mapping, nothing is added here between the assembly and the machine language, nothing is added, and this job is done by the assembler, what we call assembler, and there's so many different types of assemblers. And the translation from high level languages to assembly language is done by a compiler translation. That's why we translate from one language to another. Think if you know a friend that is German and you're American, and you speak English, he speaks German, and there's no common language between both of you. Can you understand each other? No, you're going to need a translator or a compiler to translate either English to German or to translate German to English, so you can understand each other. Let's see. Here, let me go into detail on this, and this is, guys, for you. This is really important to know the whole process. You write a C++ program. What happens when you compile it? The first thing you do when you do build, remember on Visual Studio, that's compilation. It's second, the syntax. But is there anything done before that? There's 4 things that are done in a compiler. First thing is pre-processing. Pre-processing. And what do we mean by pre-processing? You remember the include files? Include. Let's check a small program. Let's go to and here and do clear, and let's do nano program 1, is it? Let's see what's this. Okay, it's a regular program that's printing what? First name, last name, major, and school name into the console. What do you think? Is this, when it translates to assembly, how many lines of assembly code do you think it's translated to? Look at this. Let's go back and see the first step. What did we say the first step is? Pre-processing. And we can do that by, the pre-processing is including the library, the IO stream library that we have, input output stream library, and this file is gonna be huge. It's gonna be a big file. Let's go and check it. This is how we do pre-processing, including the IO streams, G++-E, and the program name. And what does this mean? Meaning an output. This is file streaming in Linux. So let's see here. We wanna pre-process, include this library. Look how many how many lines of code you have. Let's exit and let's do, it was G++, that's a compiler, dash minus E, that's an option, and program 1.cpp, and I'm gonna write it, let's say, to Gaith.pre. It's gonna be a huge code. We can see the file Gaith3 here. Let's open it now, and let me open it in gedit, and we're gonna say program or Gaith.pre. See, how many lines of code was that one? The previous one. Oops, we should have done that. That's good, we didn't do anything. Look at this. Let's include the lines here. It can give me the number of lines. See how many lines? Oops. 17,500 lines of code. And here's your code. That's only your code using namespace. This is program1.cpp, and all this was added by the pre-processing step, which is including the include IO stream library, which has the input, output, C error, all of those. That's the first step in compilation, pre-processing. After that, what happens? Let's see. Let's go back to the slide. After that, the compilation, where we have G++-O program.cpp, and this is what happens when you do build on Visual Studio. When you will do build or rebuild, this is compilation, and it's just checking the syntax, the grammar, is everything right or everything declared good. Assembling, translating what? .cpp code to assembly code, and let's see how does that happen. We're gonna do G. We already have the command, so I'll put here, and I'm gonna do that to program1. Let's do list. See this program? Program1.s. This was generated by, we didn't have it here. Do we have it here? No, it was generated after we did this. And what's that? Nano program1.s. It's the assembly code for the previous program1.cpp. A string, and this is, what is it used in push Q? This is pushing into the Q. This is the register. Move, okay. Move L. Okay, we're gonna take we're gonna cover what this means. So now we did the assembling, first pre-processing, compilation, then assembling, then what do we do? The linking. What's the linking? Linking all the object files, all the execution files, or if you have other programs. Let's see what happens here when I do the linking. What was it? The linking dash, oh no, linking dash C. Okay. Where did it go? What, do you see any new file? The O file, .o, the object file or operation file. They call it operation file because it's all operation. What do you think if you try to open this code? Can you open it? Let's do nano and see how it looks like. Nano program 1.o. See, what's this? What do you think is on? Can you read anything? This is in binary and it can read it. So That's why it's looking that way. We can use an file to hexa converter, and if I browse and take this file, I took the hello world, which is this one, and I converted it to hexadecimal to this. It was looking like what we had here, like this. You can't understand it. There's no way you can think of it. You have 17,500 lines of code, which is translated to binary and instructions. Binary and its instructions. That's why they call it operation code. Operation code, or the instruction code. And it's the executable, which is going to be executed by the CPU. So now exit this. Let's do clear and go back to the slide and check. So this covers what happens in the compilation. No, come on, don't do that to me. I think my machine is getting hot. I recorded lots of videos today. It's not even allowing me to. So here we took program1.cpp. We ran it using what? G++, G++ compiler -E to do what? The pre-processing, to include the include IO stream and convert that code to C++ and include it with our code. Then we did what? G++ -O, and that's what? Compiling, which means checking the syntax of the program. Grammar, is it good? Semantic, is it good? And then we did G++ -S, converting it to assembly language, and from assembly we did G++ -C to convert it to machine language operation code, and it was all binary. We used the converter online to convert it to this. So this looks what? Like that code, and this is a huge code. So think if I gave you this and told you to figure out what this code is, are you gonna be able to do that? It's gonna be a hard, tedious, and this is for a small program. So that's why we have assembly language. It's really good for reverse engineering. If you take a code like that, so you can understand it, translate it to assembly, and then you can translate it to high-level languages easily. So let's go to the slides. I don't think they're gonna show again. Okay, pre-processing. This is the big picture. Please guys understand this. This is really important. Now let's see. Compilers. We have two types of we have compilers. Translate the whole code. They take the whole code as one piece and translate it to assembly, and then translate it to a machine. We have interrupters, which are the same as compilers, but they take statement or instruction by instruction. They take the first instruction, translate it, and convert it to assembly language, and then okay, Daddy, I'll come in a minute. Thank you, Daddy. Love you. Bye. Love you. And interpreters and compilers. A principle of interpreters are slower than compiler because they take one instruction, translate it, execute it, and in compilers we take the whole code, all of the instructions, translate them, and then run them. This is a really important concept, which is principle of equivalent of hardware and software, and do you remember that? So now I'm going to go into a quick review. What do I mean by principle of equivalent of hardware and software? anything we can do as hardware, we can do it as software. Why? Software is translated at the end to 0 and 1, and hardware is what? Transistors, 0 and 1. And we're gonna see that when we take what? Boolean algebra. We'll see what's a transistor, what's a gate, what's an integrated circuit, and vice versa. Any software can be translated to a hardware, and any hardware can be done as a software. Which one should we pick? If you want to do something, are you going to do it as a hardware, or are you going to do it as a software? For example, there's some algorithm in cell phones, and let's say the error detection and correction algorithms in a cell phone. How do you think they do them? Do they do them as software, or do they do them as hardware? And why do you go hardware, and why do you go software? Hardware is faster. So in communication and smartphones, error detection and correction algorithm are more preferred to be as hardware. Hardware is faster, really fast. Software is slow, there's compilation and all that. But if it's changing a lot frequently, it's preferred to do it as software. Software gives us the flexibility. We can change it easily. It's a code program. You go, you change it, execute, and you're done. In a hardware, no, you have to. The integrated circuit goes, I think it takes about 12 to 18 months to manufacture one integrated circuit, so it's a huge process. So if you're changing a lot, it's not recommended to do it as hardware. You go to flexibility. Software. So software is more flexible, but hardware is faster. Now, is assembly portable? What do we mean by portability? What I mean by portability, if I take one assembly code from this machine, from my machine, and run it on another machine which has a different architecture, is it gonna run? Portability? No. Assembly is not portable, meaning I can't run. But if you take high-level languages, Java, let's say, Java is fully portable. If you take any Java code and go and run it on any machine, it will run if you have the Java compiler. But assembly is different. We have different assembly languages, and you're gonna see online different codes. You're gonna see now how NASM and MASM, they're close to each other, but you're gonna see the differences. One is for Linux, Unix, and one is for Microsoft. MASM, Microsoft, and that is nationwide. Why learn assembly language? Some errors are hard to debug in high-level languages. You might find some errors in C++ code. You don't know. It's there where you have a high level of abstraction. So you need to go deeper to solve the errors. This is fixing the errors. Assembly is faster for sure. You can embed some assembly code in a C code to make it faster, instead of having all of it as C code or C++. Better understand high-level languages, and this is the most important for me or for you guys. When I teach you assembly, I want to teach you the programming so you get more familiar with C++ and stronger, and you're gonna see, you're gonna enjoy it. You're gonna think of C++ in a different way. It's also good for reverse engineering. If you wanna reverse engineer a code, figure it out, all that, you go one level lower than high level languages. Now, we talked about data representation. What types of data we have? We have, for example, characters or strings. We have positive numbers. We have negative numbers. We have rational numbers, which are float and doubles. All those, how are they represented? We have also multimedia, like videos, graphics, all those, but we don't need them in assembly for now. So we'll take them in other classes, but in this, those are the four most important datas that we're going to be using. Characters and strings. how can we represent a character and string? Now, what do I mean? How can I represent it? If you press A in the keyboard, how is the computer gonna understand it? Remember, computer is a machine. It only understands 0 and 1. So I have to translate this A that you pressed on the keyboard to machine language, 0 and 1. And A in decimal is 65, I think, and we can go check that in the ASCII table. If you go check it, we can represent characters in 3 different ways. ASCII, and there's also other British BDC, I forgot those. There's other algorithms to represent it. ASCII is American Standardized Character Encoded, and it's 2 to the power 7. It uses 7 bits to represent each character. 2 to the power 7 is 128. So I can only represent 128 characters. Is that enough? It's enough for English. But is it enough for English and Arabic and Indian and all those other languages? No. So they extended it and used extended ASCII, where they added 1 more bit. So we had 8 bits to represent a character. 8 bits will give us 256 possibilities, 256 characters, 2 to the power 8. Was that enough? No. So they went to Unicode, which is 2 bytes. 1 byte is 8-bit, which is extended ASCII. 2 bytes is 16-bit, which is Unicode, and it's 65,000. Is it 65,635 or 65,536, something, but it's 65,000 plus characters, and that is enough. So this is how we represent characters. But how do we represent strings? Strings are what? Are an array of characters. So they go back to characters again. Positive numbers, you remember how we took it, how we represent them in binary. We can either divide by 2 or use the positional notation, and we can convert it to binary, to hexadecimal. Hexadecimal is base 16, 2 to the power 16, so we group into 4s. All that is covered, guys, in the videos. I have about 6 to 7 videos. Go and check them to cover all of this. Negative numbers, we have the sign representation, where I have 1 bit for the sign, the most significant bit. And which one is the most significant bit? The one with the one that has the highest value, the one on the left. That one is reserved for the sign. So I have 1 bit for the sign, and the rest is for the range. Sign representation. We have then 1's complement, and we have 2's complement. The problem was with sign representation and 1's complement representing -0 and +0. Those are the same number, which is 0. But in sign representation and 1's complement, they have 2 different representation. Let's think of sign representation, and let's say I have this sign representation. This bit is for the sign, most significant bit, and I put it as, I want to represent -0. I'll put it as 1 meaning negative, and I'll add all zeros, and I should have 7 zeros. And what about +0? It's gonna be 0. This is 1, this is 0, and then all zeros here. Sorry. So I have 2 different representation for 1 number, and that's not acceptable. Why computers are dumb, think of it. They can't do anything. 2's complement solved that problem. And if you go find a -0 and +0 and 2's complement, you'll find they're the same. Rational numbers, where we have division, 5/3, 3/5. Decimal points. Example 10.5, 0.567, and we showed how we can represent this, and there's a whole video on this. We can represent it in two different ways: the IEEE 754 single precision model, and this is divided into three parts. The sign, this is the sign, this is the exponent, and this is the precision, how precise the number is, how accurate. This is the range, and this is the sign exponent. And we took how to translate it to binary, how to represent floating points. This is, if you remember, in C++ we had a float and we had a double. Yeah, this is a float. A float is 4 bytes, so this is a float. Single precision is a float. Double uses double, and it's 8 bytes, and this is double. In assembly it's real 4 for float and real 8 for double. For long double it's real 10, and this is in assembly, it's gonna be REA. Oh, sorry, this is the first time using this, so real 4, real 8 is double. And now you have to know, you have to be good in converting between bases. Bases, base 2, binary, decimal base 10, hexadecimal base 16, octal base 8. You need to know those stuff. You need to know the addition and subtraction between addition of binary, addition of hexadecimal, addition of octal, and the subtraction of all those. We also talked about Boolean operation or Boolean expression, or how can we represent Boolean algebra. We said we can represent it in three ways: either an equation, a Boolean expression, or we can represent it using logical diagrams, using gates, or we can represent it using a truth table. And this is what a circuit. What do I mean by a circuit? An integrated circuit that implements any function. A CPU, a GPU, a calculator, all those are integrated circuits. They're built by using gates. What's a gate? An AND, an OR. We only have 6 gates. 6 gates, we can build any integrated circuit. What's a gate? It's a collection of transistors. So if I tell you what's the building block of any electrical device, it's a transistor. A transistor is a switch. A switch, 0 or 1. This is a transistor. A switch, 0, 1. If this switch is closed, it's a 1. If it's open, it's a 0. True, false, high, low, on, off. This is how to think of a transistor. That's a 0, 1. That's the language of a machine. And from transistors we can get gates, and can be considered as multiplication, but I prefer not to do that. Or the NOT gate, the NAND gate, the NOR gate, and XOR. Those are gates. We can build from them any integrated circuit. Integrated circuit like a CPU, GPU, FPGA, all those are considered integrated circuits. Components of a computer: a CPU, central processing unit, it's the brain of the computer. Then we have memory. Remember the von Neumann model? Don't think I'm going to cover everything here in the slides. You have to go back and read. CPU, von Neumann model, stored concept programming to enable us to store programs. That's where computer came from. I have a CPU, we have memory, and remember the memory hierarchy. Memory hierarchy is really important. On top we have registers, cache L1, cache L2, then we can have cache L3 if you want, RAM, random access memory, and hard disk, and know the difference between them. And I have then input output devices. So 3 components for any computer or any machine: CPU, memory, input output devices like a monitor, a mouse, a screen, keyboard. A central processing unit consists also of three parts: arithmetic and logic unit to do arithmetic and logic, bitwise binary operation, and we have the control unit to coordinate and do the give the control signal. We'll talk about that later. And we have a clock, synchronize the operations on the CPU. Now in the IA32 instruction architecture, we have 8 general purpose register. And guys, this is really important. If you don't know the registers, you're not going to be able to program. We have 8 general purpose registers, each is 32-bit. This is a general register, 32-bit, 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 and those are 32 bits also. We have 6 segment registers, which are 16 bits. So this is 2 bytes, each of those 2 bytes. Each of those is 4 bytes. And we have 2, let's say, dedicated registers, E flags and EIP, meaning what? Extended instruction pointer or program counter. Instruction pointer or program counter, it holds the address of the next instruction to be executed. The address of the next instruction to be executed. This makes it faster when I have it at when I have the address on a register. It makes the process faster. Now let's go back to the general purpose register. I have the accumulator, which can be used in most calculation, addition, subtraction. We usually use the accumulator. It can be divided into what? 2 bytes. It's 4 bytes. I can divide this, and this half is called what? AX, which is 2 bytes. 2 bytes are 16-bit. Then I can divide this 2 bytes into 1 byte each, which is AL and A high, AH, A low and A high, 1 byte each, 1 byte each. So now let's we can't apply that on all registers. It's only applied on those 4 registers, which sometimes they call them, other books call them data registers. Data registers. This is the extended accumulator, 32-bit, 4 bytes. Extended base register. It's a regular register that can use for data. And we have the E counter, ECX counter register. And we have EDX, data register. Data register. It can also be the input output pointer. We have the EBP, extended base pointer, extended stack pointer. Both of those will determine our stack frame or for the program. And this is when you call a function in any program. This function is going to go on a stack. That's where we use the push pop. And when we, okay, you're not going to be taking it in with me, but I'll explain that later in more detail. I don't want to confuse you now. We're going to use those two. This is base pointer and stack pointer. This is extended source index, extended destination index, and we can use them as indexes. Remember, E flags has what? A 32-bit. Think of it. This is divided to a 32-bit. Flags like carry flag, overflow flag, sign flag, parity flag. We'll talk about flags also later on. The segment registers, 16-bit segment registers. We have CS, which is code segment. stack segment, data segment, extra segment, and I honestly forgot what are those two for. Code segment will hold the address of the code, where the code is. Data segment where the data is, and the stack will hold the address of where the stack is. So now let's go and see what we have after this. We have now we're gonna go to assembly language. Remember, guys, you need to go over all that. That's really huge, how to represent floating points and all that. Please, if you don't know it, you're not gonna be able to program. Assembly is not easy. There's so many different assembly languages. We're taking in class MASM, Microsoft Assembler, and we're using Visual Studio for it. I don't have any Visual Studio on my machine, so I can't run it for you, but I'm gonna run it at school, record a video and put it, and I'm gonna write you a couple of codes today about MASM. MASM is the one for Linux nationwide, and I'm using it. We have JASM, TASM, and there's a Mars simulator online. If you go Google it, it's another assembly language. It's really good. I've used it before. So let's go to programming part. And if you know the programming part, you don't need to worry about anything. Understand the programming. It's really important in assembly. If you don't understand the programming, I don't see any reason why did you take assembly. So let's see. Instruction format. What is an instruction? Remember, your C++, Java program is translated to assembly. And what's Java? What's C++? What is a program? A program is a set of instructions. Instruction 1, instruction 2, instruction 3, 4, and it goes in sequence. So we have different instruction format. I can have an instruction with two operands, operand 1, operand 2. For example, move. I can have a move instruction with let's say E, A, X, and here I can have num1, let's say, a memory location. Some instructions comes with one operand, for example mul and div, E, A, X. Some instructions don't come with any operand. For example, set, and we'll take an example on that. Types of operand. We have an instruction which is a move. This instruction is going to have two or one or no operands. Type of operands. One type is registers, EAX, EBX, or a memory location, a label, num1. When you declare integer, num1, num2, those are labels. Memory location, those are your variables. Total. We have immediate, or what we say constant values, which are 15, 10 plus 4. All those are constant values. Three types of memory operands, of three types of operands: memory, register, and immediate. And we have an instruction. And if you go back here and see, I think now you're gonna get this. This is an instruction, a move instruction, and I have a register operand and a memory location operand. Here I have an instruction, I have a memory location operand. All this is what? Translated into binary. This binary is fed to the machine, to the CPU. CPU, what does it do? Fetch the instruction. Let's say move from where? We go and look in the code segment, the segment register. Code segment register, that address, we grab the first instruction there. Decode that instruction, know what it is. No, it's a move. Fetch the operand, fetch EAX and A. Fetch them from where? The data segment. Data segment register, the 16-bit register, it's gonna hold the address of where the data is. And this we said it's execute the move instruction, and then write the result back. We're moving A to EAX. So hopefully that made more sense now. Here, instructions. Some of the instructions that we're gonna be using: move source, let's say A for example, to destination EAX. So it's like saying EAX equals, and here I can say A. We're just moving A to EAX. For example, we've all done this in the first program. We're moving offset of string 1. What's the offset? The base address of a string, meaning where the first letter is. So if my string was Gaith, Gaith, I'm moving the address of the first letter G, where G is, I'm moving it to EDX. And then we do the call write string. An add instruction is adding what? The source to the destination and saving it in the destination. For example, add EAX and 15. What is it gonna do? Add the EAX and 15 and save it in EAX. Sub, the same thing. Subtract EBX, ECX. What does it do? Subtract the from EBX, ECX and save it in EBX. And remember, assembly is not case sensitive. It's not like C. C is case sensitive. Assembly is not. Other instruction we have call a function, push, pop. This we use it with a stack. Compare, to compare between two numbers, and it usually returns either 0, greater than or equal, and then we can use the compare. After a compare, usually we have the jump. Okay, I have. If they're equal, if it returns 0, I'm comparing EAX and EBX, it's gonna subtract EAX from EBX, and it's gonna see this will give me a 0 if they're equal. That means jump equal. If they're equal, jump to wherever it tells you. Jump if not equal. Jump if 0. Jump if not 0. We have the increment and decrement. Increment, add 1, like I++ in C++, J++, num++, and decrement like num minus. And we have the jump command, and we're gonna declare arrays. How you declare arrays in C++ in assembly is really important. Let's go back here 1 minute. You have to know what's the difference between an instruction, a command, and a directive. It's really important. What's a directive and what's a command? Declaring arrays, we can do that in 2 ways in assembly. I can say list, the name of the array, byte, the data type, and I have 1, 2, 3, 4. This is what? 0, this is 1, this is 2, and this is 3. Element 3. I have 4 elements. Here we're in assembly, remember, you have more control, so you can do that. I declared the first element as hexadecimal, the second element as decimal. By default, assembly, if I don't have an 8, is going to take it as decimal. This is binary, and this is a character A. All that, each one of those is a byte, so this is going to be 4 bytes in memory. 4 bytes in memory. And we're going to use the current location counter to find the size of this array. So if I say the current location counter $, minus list. List is the base address of what? Of this, where this is in memory. So think of this. If I have this, let's draw the memory here. Well, it's not. It's out of ink. 2, 3, 4. I'm gonna try to squeeze in list 1 also, but we're gonna need more space. And let's say this is address 0 x 0 1 1 0. This is the first byte, a byte addressable memory, and this is labeled as list. List is pointing here to this address. That's what I'm. So this is gonna hold what? 10 8. This is gonna be 53, and this is gonna be the binary number, whatever I have. Sorry about the handwriting, guys. And this is gonna be A. This is 4 bytes. Before I do this, the current location pointer is gonna be at this address, pointing at list. Before I have list, it's gonna be 0 1 1 0. Now this is gonna be 0 1 1 1 11, 0 1 1 2, 0 1 1 3. And now where will the current location pointer be after all this? It's gonna be sitting on 1 1 4, waiting to inputs. So I'll have $sign 0 1 1 4 minus 0 1 1 0, which is this address. This is the current location pointer now. It's gonna be what? 4. Size will return number of bytes in memory. How many bytes did this take in memory? Now if I go to list 1, this is another way to declare an array, by having the size as word. This is the same way, sorry, this is the other way. Word meaning taking 2 bytes each element. So those 2 bytes are gonna be what? 1000 hexadecimal. Those 2 bytes are gonna be 2000, 3000. And there's 2 different ways here. There's little endian and big endian. And what do I mean by little endian? Little endian takes what? Don't worry, I'm gonna draw the memory later at the last slide. Little endian, I take the least significant byte at the lowest address. This is the least significant byte of this one. This is the least significant byte. Least significant byte, the byte with the lowest value. So here I'll have what? 0 0. It'll be saved. And here I'll have 10. Here I'll have 0 0, meaning here. Sorry, I put those because and here 20. Here 0 0, and here 30. How many elements do I have? 1, 2, and 3 elements. This array consists of 3 elements or list, each of 2 bytes. So $sign minus list 1. List 1 is gonna be pointing actually here on this empty spot. So this is gonna be this one. Those 2 bytes are gonna be for 10. This is where list 1 is gonna be pointing at, which is 0 1 1 4. And now 2 bytes, and those 2 bytes are for the 20, and I have 2 bytes, so it's gonna be 215, 216, 217, 217, 1 minute, 1 4 114, 115 is the 10, 116 is the 0 0, 117 is the 20, 118 is the 0 0, 119 is the 30, and now I'll have the current location pointer sitting at 0, 1, 20 minus 0, 1, 20, the address. This should give me what? 6. So this size in bytes 6. If I want to know how many elements, because it's a word, a 2 byte, I divide by 2 and it's gonna give me 3. It's gonna give me 3. This is the current location pointer. Current location pointer. One way to declare arrays this way, I have to use this, the current location pointer, to find the size. Now what happens if you put this line, and let's delete this, clear, erase all ink. What happens if I put this and take it and put it here? What do you think is gonna happen? The current location pointer is gonna be sitting at the address. If you remember, we had the 120, and it's gonna take the size of this and the size of this. If I had what? This sitting here, let's see. It's gonna take list the address of this one minus this, so it's gonna give me what? 10, both of those. So be careful when you declare an array. Try to find the size of it immediately. Sorry about that, guys. Here I have array word. I'm declaring an array. I named it array. It's gonna hold 2 bytes. 2 bytes. Oops. Size of it is 5 elements, and we use the dot operator. This is the size and this is the initial value. So what we did is declare 2 bytes, 5 elements of 2 bytes each of, I declared an array of 5 elements, each of size word or 2 bytes. So this is going to be 10 bytes. 10 bytes. Now look at this. This is a MASM program. A MASM program, and let's first take a really simple MASM program, and let's do list. I think I saved here template. Okay, let's go to nano template .asm. If you look here, I'll have the title of my program. Comments in assembly, we do comments using semicolons. So this, I'm not gonna need it. I'm just gonna take it out, and I'm just showing you how to comment any code. Then I'll have the include. I'm including the Irvine library 32.inc, and this is for the core read integer and core write integer. You can see those, you're gonna find them in a table in chapter 5 procedures. Then I have the .data. Here I'll have my data section, and here is my code section. In my data section, let's see what we're gonna do. What do I need to declare? For example, we want to write a program that prints your name, major, and school each on a separate line. So here's what's gonna happen. I'm gonna declare string 1 as my name, byte, and I'm gonna say you can use either single quotes with strings. It's not the same as C++. Single quotes or double quotes. So let's say Gaith, space Albadarin, and here I'll add 0 A8, 0 D8, and 0 to add this non-terminated character to the end of the string. So I have string 1. We declare string 1. If you, this is same as saying in, let's try to relate it to C++. It's like saying string 1 equals Gaith Albadarin. Oh, it's taking C code now. Now I need to declare string 2, which is also byte. I can declare it as a word, but why make it take more space? And I can say here major computer science, and here close it, and 0AH I can put 10 instead of 0AH. 0 hex A in hexadecimal is 10, and I added a 0 here just because to distinguish the A. When I have hexadecimal numbers, if I have a letter as my first number, I have to put a 0 before it, but this won't be in memory. You won't see the 0 in memory, you'll only see the A. And for the 0DH, what's D? 13, and I can have a 0 here, and then this is same as saying string 2 equals computer science in C++, and I'll do string 3 byte. Remember, it's you can do it byte. It's one, and I can do double quotes here, and let's say Texas Wesleyan, and here we can put 0, 8 or 10, 13, and 0. Carriage return, new line, and a 0 to the null terminated character added. And this is how my code here, we're not gonna use anything. Here's the template of any code, how it should look like. Now this is the code part. That was what? The data part. Now we have the code part. The code part, what we need to do first is move EDX. I'm gonna move the offset of what? String 1. The offset of string 1 is the base address, is the address of where G is. I'm moving it to EDX, then I'm saying call write string. This will print the first Gaith Albadarin. Now I need to move EDX, and I'm gonna move offset string 2, and I'm gonna do call write string. Needs to be one word, guys, be careful. Call, this is not one word. Move offset of string 2, where this, the address of C, and print until I see a 0. If we took those 3 zeros out and I did this and I only did this, it will print those 3. It will print those 3. And try it. Take this 0 out, this 0 out, this 0 out, and just have this, comment this part, and it will print all those three. Now I need to do also move edx offset string 3, and I'll do call write string, and this will should print the third string. This is, if you take the 3 zeros out, think of it, try to take all those, this one and this one and this one. This one is gonna print all three of those. This one is gonna print what? It's saying here, go to string 2 where it's saved in memory to C and print everything after it. So it's gonna print computer science and Texas Wesleyan. If you go here, if I do move offset string 3, it's gonna print this if I didn't have the zeros. And if you want, and this is like saying in C++, if I had declared it up there, I'm saying cout what? String 1. And for the 0A8, 0D8, I'm doing an end line. And you're gonna see, you think this is confusing? You're gonna see MASM. MASM, you're gonna need to do more than that. This is easy. Here you're using functions, call write string. It's letting you do this. And MASM, no, you're gonna have to program that. The call write string. I'm gonna stop now for a minute, take a rest, come back, do more MASM programs, adding 2 numbers. You know, we can do it now. Let me do it, finish it, and post this online, and I'll post the MASM after this. So I need a new, I'm not gonna run it because I don't have a MASM, but here, and let's say I need to add 2 numbers in assembly, which are entered by the user. So I can declare num1. You can do it as byte or word. Word is short. D word is an integer, and so on. And I don't want to give it an initial value, and I'm gonna declare num2. There's no semicolon here, as word, and I'm gonna declare it as 10, and no problem in the sensitivity. It's not case sensitive. And I'm gonna declare here string 1 as byte, and please enter two numbers. And remember, I'm gonna add the 10, 13, and 0, 0A8, 0D8, and I'm gonna say string 2 byte, and I'm gonna have total, or I can say sum of num1 plus num2, and I'm gonna say equal, close it. Okay, let's put space here, and 10, 13, and 0, and I'm gonna name this string end. I like always to add this in my code, makes it look better. And I'm just gonna have space, and just to have another or you can do 10, 13. And now what do I need to do in .code? In my .code section, and if you want this in C++, here what I did in C++, a word is short. I'm saying short num1 and num2, which is the one below it, equals 10. That one I didn't initialize, and this one is 10. And then I'm saying what here, I'm saying string 1 equals please enter 2 numbers. And remember, we can do this and just a regular cout by here in assembly, and this is the same thing. We're declaring a string or we're saying cout. Now here, first thing I need to do is say please enter 2 numbers. So what we'll do is move edx, and I'm gonna move to it where the p is. String 1, if there's a space, it's gonna take the space. Offset the address of the first character in that string. And then what do? Call, that's a function, write a string. So it will print please enter 2 numbers. Now I need to enter 2 numbers. I'll do call read integer, which is a cn. This is cout string, this is a cn integer. I get the first number, it's gonna go to the accumulator. I need to move it. I'll do move to num1 from ax, let's say. Yep. And then I need to do, if I want to enter the other number, I can do call read integer again, and that will let me, okay, because I said okay, I have to do a call read integer, took it to the accumulator. Now I'm gonna do move num2 to ax to num2, and still I have an ax here now, which is a register. I have num2. Now I'm gonna find the sum of those two numbers. So what I'll do is I'll do add ax, which I have in it, add the last one I had in it is num2 plus num1, and then I can, if I had declared sum up there, I can move ax to sum, but here all I need to do is what, move edx string 2, and I need to move the offset, and then I'll do call write string, and then I'll do call write integer, and I can do that for string 3, so it can give me an extra end line. Let's see how the code goes here. Okay, let's open it in a GE edit so we can see it in a better way. Here's my assembly code. His title is the include. Here's my data section. This is our data section. This is our code section. We declared our data here. Short, one variable, second variable, and those strings. So now here I'm calling the first string. Move the address of string 1, the first letter, and then print that string. We print it. Then I'm saying cn integer, which is gonna be, it's gonna input an integer in AX. Now I'm saying move AX to num1, so it's gonna save it in num1, my variable. Now I'm doing another call, read integer, which will take it to AX also, overwrite AX, which had the first number, wherever you input it. Now here will be the second number, I'll save it in num2. But remember, now that register AX still has num2 in it. We didn't wipe it, we didn't clean it, nothing was overwritten there. So to add them, what do I have in AX? Num2. I add num1 plus accumulator and save it into accumulator. So this actually equals AX equals what? Num2 plus AX, and what's this? Here I'm saying num2 equals AX. See, but I didn't, and here I'm saying cn AX. Here I'm saying num1 equals AX, and here I'm saying cn AX, and here I'm doing cout, please enter two numbers. This is the C code of it, and let's make it far here. Hopefully this helps, writing it in C code like that. And here what am I doing? I'm just saying, but here be careful, it's actually saying, or no, it's not 1 minute, it's saying num1 plus accumulator, which is num2. So I'm gonna leave it that way. And here I'm saying move edx. I'm here saying cout, what do we have as string 2? Move the first address, the address of the first character into edx, and then print call write string. And here I'll say sum of num1. Sorry about the capital letter, but I'm gonna leave it like that. No, or let's change it. Okay. That's those two. And now I'm doing call read integer. It's like saying this one is like saying cout whatever is in AX. This is assembly programming. It's so much fun, guys. If you know it, you'll be so powerful in programming. Really concentrate as much time as you can on the programming part. Learn it. Even if you during the summer try to play around with it. Try to learn different assembly language. Other MASM, NASM, JASM, Mars simulator. You're gonna be much better in C++, Java, C. They're gonna be so easy, those languages for you. I'll stop here. If you have any questions, please let me know. I'm gonna post another video just maybe in 30 or an hour about NASM. I'm gonna run another couple of examples on MASM, and the others will be NASM.